So today we're going to be learning about reactions with ketones and aldehydes, specifically to synthesize like an alcohol. So first reaction is just using a basic acid. So for this we're using H3O+. So the first step here is that our oxygen will pick up a proton, and this, grab these arrows, and this will obviously give the positive charge to our oxygen molecule, and we'll have a positively charged oxygen with our hydrogen that we just picked up. And I'll add the positive charge in here. Okay, so that's what we have, and this is still hydrogen. So that's our first step. And then after deprotonating this, we're left with just water, plus there's water in solution. So let's go ahead and draw our water molecules. Our water molecule. Nope. It's not the most fast process ever. Alright, here's our water molecule. And I'll hit draw so I can draw the arrows. And now this water molecule is going to do a nucleophilic attack on this carbon here. Why? Because this carbon is delta positive, since this oxygen is pulling electrons away from it, especially with the positive charge. So by protonating it, this carbon is more reactive for these type of things. So we're going to go ahead and draw our little arrow. That's supposed to be an arrow. Ignore whatever's on the end there. And then obviously this bond, the electrons go to the oxygen, since it has a positive charge and wants the electrons. So this is also going to have these equilibrium arrows. And now we're going to have, now that our double bond is broken up, we'll have 4 bonds. We'll have an sp3 carbon right here, whereas here we had an sp2. And we can go ahead and draw. We have our OH, that was right here. And then we added our H2O. So this oxygen will have a positive charge. Oops. Can I add another? No. Great. Give me 1 second to draw on these hydrogens. There we go. And then I'll add our positive charge. Okay, so this is what we have as our second intermediate here. And obviously the only thing left in this reaction is to deprotonate this oxygen, and we'll have our geminal diol here. So I'm not going to show that step, but I'll draw the final product really quick. All that would happen is an excess water molecule would pick up the hydrogen, and the electrons would be drawn towards that oxygen. So we'll go ahead and draw our geminal diol here. And an important thing I didn't mention yet, oops, whatever, get it. An important thing I forgot to mention was that this structure here has some very important resonance. So if we draw some resonance, can actually, I gave up using the actual ChemDraw features. Now it just looks like a mess. Whatever. So, no. Let me keep drawing. That's supposed to be a hydrogen. Just let that be a hydrogen. That's a positive sign. Okay, hold on. Yeah, so what I was trying to show, this is our species right here. This is actually way more reactive than our initial aldehyde, because it has resonance where the positive charge can be distributed to the carbon. Now, this carbocation will be really reactive with nucleophilic attacks because obviously this is an electrophile, that's a nucleophile, they want to be together. So that is kind of our first reaction. That's how we make a geminal diol right here. That's how we make this guy from an aldehyde. Now let me set up our next reaction. Okay, so here we have a ketone. I'm going to give it a little more complexity, so it's a little more interesting at least, but that really didn't work. Oh no. Whatever. Okay, so here's our weird looking molecule. But we're really just going to focus on the ketone here. So to reduce this ketone, what we need to do is take this and turn it into an alcohol, or I guess an ether would technically work too. But we're focusing on alcohols, so that's what we're going to do. And to do that, we can use two different reagents. We can either use sodium borohydride or lithium aluminum hydride, which both basically achieve the same goals. I'm going to show the mechanism for sodium borohydride just because I can. Okay, I'm going to go ahead and draw some things. So I've started drawing our mechanism here. We can see our electrons from the hydrogen-boron bond are attacking our carbon here, and then these electrons are going to pop back to the oxygen. And this is going to make... Alright, so that gets us to here, where our oxygen is negatively charged, and then we have our neutral boron hydride right here, borohydride. So, what's going to happen is these electrons are going to go pick up, oh, that's wrong, that's not what I meant to do. These electrons are going to actually pick up this whole molecule, and we're going to form an oxygen-boron, like, ether, I guess. So I'll draw that weird molecule. Okay, so this is what we get from the oxygen attacking the boron. We get this molecule, and what's actually going to happen is this whole thing is going to happen 4 times. So this boron will kind of be the center of 4 organic molecules, and then they're all going to pop off like simultaneously once acid is added. So we'll go ahead and show our little reaction arrow for the acid. We'll say H3O, whatever, plus. So what's going to happen is this boron, or, there'll be no hydrogens left because they've all left, and the boron has 4 connections to these oxygens. So it's actually going to pick up, it's actually going to pick up protons 4 times from the acid, and that's going to make it pop off of our oxygens, and we're going to get our final product, which is going to be a reduction of our ketone or aldehyde. I can't use ChemDraw. Oh jeez. Oh jeez. That is not what I meant to draw there. No! ChemDraw. Okay, there we go. That's what we will have. One of these will be a hydrogen that we added. And that's our final compound. Yep, pretty interesting. Pretty fun. Alright, our next reaction. Okay, another way to make alcohols from ketones or aldehydes is using this sodium cyanic kind of compound. So, what's gonna happen is obviously this is gonna attack our delta positive carbon right there, and there our electrons go to that oxygen. We've seen this before. And that will make, obviously, the addition of our cyano group. Oh my goodness, I hate ChemDraw. Yep. 1 second. So this will be our C, and this will be our O, and our O will have a negative charge since since it gained electrons. And so what we're going to do is try to protonate that oxygen with HCN, and the oxygen is going to go ahead and steal the hydrogen from this compound, creating our reactant again, or our reagent, I guess. And that will give us our final product of an alcohol with a cyano group. Not sure the official terminology there, but it's definitely not what I just said. Alcohol and CN. So there we have our final product. Probably very toxic, but pretty fun. Okay. Alright, here's what we have for our last example of how to make alcohols from ketones or aldehydes. This is with a base. So instead of initially protonating this oxygen, we're actually going to start with our nucleophilic attack. And this will obviously kick these electrons up to the oxygen. That's supposed to be double-headed. And then we'll get an O minus. And, oops, I forgot one guy right here. Our OH will have added and now be neutral. So obviously this oxygen wants to pick up a proton, and it will do that with another, with the conjugate acid of OH, which is just water. So I'm just going to write out H2O to make it easy for myself. And then we'll show that our oxygen picks up an H, and that goes to the oxygen. So our final compound will look like this. So it'll be another geminal alcohol, or whatever, a geminal diol, sorry for my mispronunciation there. And then plus OH that we just formed from the water. That's not what OH looks like. This is so hard to do. Okay, there we go. So there's our geminal diol that we formed from a basic reaction. So yeah, you can use OH minus or H2O plus to make these geminal diols. The mechanisms are honestly the same, except acid has the protonation of the oxygen before the nucleophilic attack, and like I said, this one does the opposite. So yeah, that's it. Have a good day.